To continue with the Claisen reaction, we looked at self condensation reaction of Claisen, and now you should be able to do these couple drill problems. And we're going to move on to look at mixed or cross Claisen reactions, and it's basically same as when you were trying to do cross aldo reaction. So what you want to use is esters without alpha hydrogens to avoid having 4 different products of Claisen reactions. So if at least one of them cannot serve as a nucleophile, then you're limiting the number of possible products that you could produce. So some of the examples of these are esters in which it's attached to a phenyl group, because this carbon right here doesn't have hydrogen. You could have a formic derivative of ester. And another example is an ester that looks like this, where that won't have alpha hydrogen either. Another method is to use LDA to form the enolate first, and then treat it with a different ester. So this would have to be done sequentially. So if you have one ester and then you treat it with LDA, and you would have enolate at this carbon, and then you could react with different ester, and then you would form the crossed Claisen. So in this example, you would make a carbon-carbon bond between this carbon and this carbon, and you know that the O minus forms, and then O minus comes back down, kicking this OR off. So this carbon is this carbon, and then you got 1, 2, 3 carbons coming off of it. 1, 2, 3. So that would be the product of mixed or crossed Claisen reaction. If you're doing a Claisen reaction in an intramolecular fashion, then you would be doing what's called Dickmann cyclization, and that's in the next page. But before we go on that, you should be able to do reactions like this and be able to give me products. So next is the intramolecular Claisen, in which we have both the two esters all in one group, one compound, so that it could do a cyclization. And here once again, like you saw in a cyclic aldo reaction, you want to form the enolate and react with an ester so that it will form either the 5 or the 6 member ring. So in this example, you're forming an enolate by deprotonating this proton to form this enolate, and then that is going and attacking this carbonyl of that's within the same molecule. So you're forming this bond right here, and then the O minus comes down, and then it kicks up the ethoxide, so reforming the C double bond O, and then this proton is very acidic. So the base is going to go and grab that and form enolate anion that is in between the two carbonyls, which makes the it drives the reaction to that, because this is a very stable compound. And then If you protonate it, then you get the neutral product, which is a beta keto ester. So you could try to do this with, deprotonating here and then reacting here. That would give 1, 2, 3, 4, 5 member ring, which would be the same product as what you see, right? So at this point, you should be able to do 22.28, 22.29, and 22.31A. I'm going to move on to looking at how to do synthesis using Claisen, but before you attempt to do these problems, what I want you to make sure is that you know the forward reaction. Be able to do problems like this, or the drill problem, before you even attempt to do synthesis using Claisen. All right, so just like aldyl reaction, in which if you saw alpha beta unsaturated aldehyde ketone or a beta hydroxy aldehyde ketone, that triggered you thinking about doing aldol. For Claisen, the functional group that you want to recognize is the product, which is beta keto ester of some sort, or it's possible, since now you know the hydrolysis reaction, that this could be in a form of beta keto acid as well. So that's the functional group that you're thinking. So whenever you see those either one of those functional groups, then you should be thinking about using Claisen. So here's an example of a synthesis problem. Let's say you have this compound that you needed to make. So once again, this is easy because I just already told you what functional group to look for in order to think about Claisen. So you see the carbonyl at the beta position, and then the ester. All right. So we know that you have to think Claisen when you're thinking about, when you recognize this functional group. So Claisen requires that you have an ester nucleophile, and then an electrophile that's serving as an ester that's serving as an electrophile. So that the question is, then where did the carbon-carbon bond form in forming the Claisen? And it's usually the alpha and the beta carbon. So this is the bond that we're trying to make in doing Claisen. So this part in which the ester is intact is probably where the nucleophile was. In other words, that was the enolate. And it must have reacted with this part, which is the electrophile. So in other words, that must have served as the ester that the nucleophile has reacted with, and this part got kicked out in order to make that carbon-carbon bond. So then the question is, how did this enolate come about? And probably the easiest way to make that without doing a self-condensation is to use LDA. And so you would start with this ester, and then because this is a very strong base, it's going to grab one of the protons, alpha, to it and make this enolate, and then you react with those. All right. The only difference, if you recognize, if you were given a carboxylic acid as a product that you were supposed to synthesize, then your problem would be just one step longer, in which then you would have to do a hydrolysis reaction in order to have to have the product. So for example, in this case, let's say we had to make this. So you recognize the alpha beta beta carbonyl carboxylic acid. If you were to make this, you know that this must have come from an ester. It doesn't matter what kind of ester it is, but hydrolysis of an ester produces the carboxylic acid. So then this now problem becomes this kind of problem where you ask the same question. I recognize the beta keto ester, so then which part came from the nucleophile? So we're trying to make this bond right here. So this must have been the my nucleophile in which you produced it by reacting LDA with this compound to form the enolate, and then the other part would have been another ester. So remember that carbon-carbon bond is formed, so this carbon is the one that had the ester that got kicked out. So here's my nucleophile and here's my electrophile, and going forward you react this, you get this, and then you take this, you hydrolyze it, and you get this. So you're basically doing the same thing over and over again in synthesis problems. You take whatever compound that you're asked to make and just think one step backwards. How did I make this? From what? Okay, and then once you've accomplished that, then and treat it as another synthesis problem. So how do I make this? And that's when you should be thinking Claisen in these examples. So hopefully you're able to do these synthesis problems, cyclization problems 22, 28, 29, and 31A, and be able to come up with the starting materials that gave the product in these cases. All right, and make sure you remember to make 3x5 cards for both Aldo and Claisen, so that you become familiar and keep quizzing yourself as to what the forward and backward reactions are.